then the Thursday's class, which despite this delay will take place, I will just talk about what we can do if the problem that we need to solve turns out to be NP-complete. What kind of fallbacks do we have? Okay, so I'm going to start with one of my favorite applications of network flow. It's not so difficult or even very different from what we've seen before. What makes it one of my favorite applications is that this is actually this is an actual application as opposed to a potential application. So, a number of years ago, I was walking down the street and bumped into an alumnus, a student who had been in some of my classes, and she said, I'm glad I bumped into you because I'm working at the medical center, at the UCSD medical school as a programmer, and I need to solve this computational problem, and it seems like it's a huge number of possible solutions, and I don't know how to search through them all. So here was what she said was the problem. So she's trying to design a bunch of medical experiments. So you have a bunch of patients that have registered to take part in these experiments, and you have a bunch of studies that are the experiments. And so each study has its own requirements for who can be part of the study. White males between 30 and 60, or people who don't have high blood pressure and haven't been on the following medication. Okay? So each one has sort of a different set of conditions. There's really no way to make sense of them except to say, for every patient we can test, in every study we can test whether the patient is suitable for the study, and that gives us a bipartite graph between patients and studies where we put in an edge if the patient can be part of the study. So in addition, there's this kind of requirement that you can't sign up a patient for too many studies. I guess patients have a limit in patients. They're not willing to be subjected to too many things. So there was this number K that was part of the input that determined how many studies each patient could be in. And then each study, on the other hand, had a certain required number of patients, RI, that the study requested. And so the question was, is there a way of assigning patients to studies so that no patient is assigned more than K studies, and every study gets at least its requirement number of patients? So I immediately said, this looks like a network flow problem. Let me just work it out. And how did I know it was a network flow problem? Well, sort of like look at special cases. Maybe look at the special case when K equals 1, for example, and where each of the RIs is 1. Okay. So then what are we looking for in terms of this graph? A matching, a perfect, so like a right perfect matching. Okay. So that sort of suggests that we should be able to generalize the method used to reduce flow to matching to flow in order to reduce those problems of flow. So let's see, in matching we added a source node as that isn't the same as a study. And we added a sync node, and then every node on the left, we put an edge between the source nodes, and every node on the right, we put an edge to the sink, and then we directed all the edges in the middle from left to right.
So don't you have the possibility that some patients aren't going to be in any studies?
That's true, but that actually wasn't one of the constraints.
Okay.
If someone volunteers but they're not, it could be that they're not suitable for any of the studies.
So you wouldn't have the same number on the source sensing?
Well,
like you'd have more people on that side.
Yeah, we could have, potentially we have many more patients than we have studies, I think would be the typical case.
Okay.
And, maybe like the required number of patients per study might be 1,000 and K might be like 3, because you don't want to be in so many studies. Okay. Okay, so now the remaining thing to do is we sort of define the graph, but now we need to define the capacities. So what should we use for capacities? We want to make sure that, okay, so every patient in every study, how many times do we want to assign that patient to a study?
Once.
At most once. So what should the capacities of these edges be?
One.
That's the easy part. Well, actually, now the other part's not so bad, right? So now we want to make sure that we're using at most K of the edges coming out of every patient. Yeah.
But K, if the edges are from S to each T1 to Tn has capacity K?
Yeah. Good. And then Ri, because we don't want to, or we don't get credit for assigning more than Ri patients to a study, and we can always reduce the number of patients in a study. So, okay, so this gives us our flow graph. So from the initial problem, all the numbers and the bipartite graph, we constructed this flow graph. So from our input, we construct the flow graph. A flow network, I should say. Okay. And that has all the ingredients of a flow network: the edges, the capacities of every edge, the start node, and the end node. And the second thing is we need to say, now for solving flow as a black box, we need to say something about this flow is equivalent to our original problem. Okay. So if there is a flow F, when is it going to be good enough to solve our problem? Equal to the sum of the RIs. That means every edge here is used to full capacity, which means that every study is been given its required number of participants. Hey. So we want to say if there is such a flow F, so we solve the max flow problem, we get this flow F. If it meets this requirement, then we want to say then we can use it to produce a legal assignment. To patients' studies meeting all the requirements. Okay. So if we do this, are we done? There's one other thing we need to say. Because what if there is no flow? Then what should be the case? So if the max flow F has flow less than the sum of the RIs, what do we want to be the case?
Want to maximize the flow.
Well, So we find the max flow. Okay. If it meets all the if it's enough flow, then we can use it to make an assignment that meets all our constraints. But what if we find the max flow and there isn't enough flow? Then we want it to be impossible. And we want to say there is no assignment that meets all the constraints. Well, arguing a negative is sometimes hard. So
there should be a way to say that at least some of the studies, the best we can do is assign most of the studies
yeah,
patients required.
we could reduce the requirements and hope, remove some of the studies and try again. But saying here we're trying to satisfy all the studies. So using this as a black box, then we can just say, if it's impossible, what do we do next? We don't throw away everything. We try, maybe increase k by 1. Say, can we do it now? But that's up to the user how they want to do it. Saying the correctness of the algorithm is saying if we try to find the max flow, or we find the max flow and it doesn't automatically satisfy all the requirements, if we can't apply this, then it isn't because the max flow didn't work, this approach didn't work, it's because the set of requirements was too strict. There is no solution. That, it's impossible to satisfy those requirements. Now, trying to argue that something doesn't exist is often fairly difficult. So let's rewrite this in a logically equivalent way. Okay. Saying if something then not something. So saying if there is no flow that's big enough, then we want to say then there's no assignment. What's logically equivalent to, if not P, then not Q. If Q, then P.
So if an assignment
exists. So if an assignment exists, then there is a flow. So this is the direction everyone forgets. Because this one you actually need for your algorithm. You need to say how given a flow you produce the assignment, because that's what you actually want, is the assignment. But this part isn't really part of the algorithm, but it's an important part of the proof of correctness. What we need to do, actually doing it is pretty similar to the bipartite matching case. Yeah.
Why do you have a greater than or equal to sign? The flow can never be greater than.
It's true, but this is the important direction. Yeah.
Okay.
So it'll actually be equal to.
Okay.
So whichever you prefer. So we assume, so let F be a flow with equaling the sum of the RIs. Then so we from this we're going to create an assignment. So when do we assign a patient PI to study SK given this flow? How do we use it?
Yeah. They meet the requirement.
Well, first we need to define the assignment and then show that it meets the requirements. So how do we use the flow to define the
Is it if there's an edge less than or equal to 0, is it then assigned?
less than or equal to 0 or
Equal to 1 to assignment.
If there's no edge between Sj and Pi and the flow of Pi is less than k.
okay, but
That's good.
maybe I should draw the picture again. Sorry, I erased it.
If the incoming edge is equal to 1, then
Yeah.
that patient is assigned to that study.
Right. So what it looks like is we have, for patient I, is we have one edge coming in of capacity k, okay, and then we have any number of edges going out to the different studies, and saying the flow, each of these edges has capacity 1, which means the flow will either use it to, I'm assuming the flow is integer valued because the Ford-Fulkerson method always finds integer valued flows. I should have probably said that explicitly. Okay. So the flows are integer valued and the capacity is 1. So some of these edges are going to have flow on it and some not. And it's the ones that have flow on it that tell us which studies to put them in. Okay. So if there's flow from Pi to Sj, then we assign patient I to study J. Okay. So so now we need to show that this assignment meets all the constraints. So we have two kinds of constraints, that patients can be used in most case studies, and the second one, the studies have at least their required number of patients. So why can the patient be used in most case studies?
The flow of Pi is at most k.
So the incoming flow is at most k because there's only one edge coming in and its capacity is k, which means there can be at most k edges that are, k capacity, total flow coming out, which involves at most k edges. So since the flow into Pi is less than or equal to k, at most k edges out of Pi have flow 1. So each Pi is assigned to less than or equal to k studies. So that's one part of the constraint. How about on the other side, when we look at the studies, why do we know that the studies get at least Ri patients?
The sum adds up to the sum of the RIs.
Right. So because the flow of F is the sum of the RIs, each edge from, that's equal to the incoming flow to T. Each edge from each Si to T, Sj to T, is used to full capacity. Okay. Therefore, each study has at least Ri edges with flow into it. In fact, exactly Ri edges would flow into it, i.e. gets assigned Ri patients. And each edge And here in this step, we're using the fact that the capacities of these edges coming into it are all 1. So the total flow through that node has to equal the total number of edges being used. Okay. So I guess I need to rewrite this. Okay. So every study, write that somewhere bigger. So each, the confusing thing is that in this problem, as in a lot of the other problems, sort of our map from flows to assignments is just going to be invertible, and we're really just going to be talking about the same map in the other direction. That's not true all the time, but it's true most of the time. And so it's just confusing because it looks like you're just showing the same thing over again. But logically, it's a little bit different. So what we're saying is, now, this was saying if we had a flow, how we create an assignment. If we have an assignment, how do we create a flow? And it's really the same equations, just sort of, but the logic is split. Okay. So here we're saying from, we assign patient PI to study J if and only if PI of Sj equals 1. Okay. Now it's going to be the same relationship. It's just now we're just using this instead of to define the assignment to define F. Okay. So set F of PI Sj equal 1 if patient PI is assigned to study Sj. How about the other edges? To make it a flow, what do we have to, we have the source to PI. What do we have to, how much flow do we have to send from S to PI? From the, so we have to balance the incoming, so this is our rule for when we're trying to send flow across that edge in the middle. To conserve mass, what do we have to do? It's not, well, what if the patient is only assigned to 2 studies and K is 5? So we assign it to 2. The number of studies, it's really forced. The number of studies PI is in. Okay. And what will the flow from each study Sj to TB it just has to be Rj. Because we have to have it be full. So it's going to hopefully be the number of, which should be the number equal to the number of patients assigned to Sj. Okay. So if we've got any assignment, we use these values, and here we argue that because the flow had conservation and met the capacity constraints, that it met the constraints for the assignment. Now we just do the same reasoning, but in the reverse direction. We're arguing that since the assignment met the constraints, the flow will have conservation and will meet the capacity constraints. Yeah.
Does the flow from Sj to T has to be equal to Rj? Could it be larger than Rj? Because that way it has the study Sj has at least Rj.
Okay, so I should say what we'll do, if we have an assignment that gives study SJ more than RJ patients, we can just delete patients until it's equal to SJ. And so that doesn't really change. That doesn't increase the number of studies any patient is in, and so we'll meet the requirements exactly. Otherwise, this construction is going to break the capacity. If you have to do that, or else it doesn't actually correspond to a flow. But so I should have mentioned that explicitly. Okay. So okay. So really, it's just we're working through the same kind of equations in the reverse direction. Now we've met capacity, so we have conservation here because we assigned the incoming flow equal to the number to the outgoing flow. We have conservation here because the incoming flow is RJ. So flow is conserved by construction at each PI is conserved at SJ because the incoming flow equals the number of patients assigned by the rule, and that equals the equals RJ because we're assuming the assignment gives each study exactly its requirement number of patients, and that's equal to the outgoing flow by our construction. Yeah.
So where it says the number of studies that patient PI is in, should there be a sum there from all the studies coming back into PI? Is it like the sum of all the edges coming into?
What's these edges coming out of PI?
The one below that, just below.
Or SJ, you mean?
Yeah, so that should be the sum over all J. Right?
Well, that's going to equal or just RJ. So we're saying that's equal to the number of patients assigned to SJ, which we're assuming is by the validity of the assignment is equal to RJ, the required number. Okay. So we can just we could say it's equal to the number of to the number of incoming edges, or it's equal to RJ. At some point we have to argue that those are really the same.
Okay.
So whether we use one as the definition, which one we use as the definition, either way we have to show that the two happen to be the same. Okay. So that means we've conserved everything except PI and SJ are everything except the source and the sink that don't need to meet conservation. This shows all the conservation requirements are met. Capacity. Okay. Well, we've assigned the flow 1 in the middle, so that meets the capacity because all the capacities of the edges in the middle are 1. Okay. And because we have, if we assign PI to SJ, we must have an edge between PI and SJ. So there must be an edge of capacity 1. So these are actually using edges that exist in no more than capacity. The capacity for constraint for PI is met. Why? Because what did we say for the edge S to PI is met? Because the capacity is K, and the flow is the number of studies PI is assigned to. PI is in, and we know from the validity of the assignment that that's at most K. So because each PI is in at most K studies. And finally, the flow, we need the flow of this constructed one to equal some of the RIs because every edge into a T is used with full capacity. And that's right here from our definition. Okay. So we showed that given an assignment, we can construct a flow. The flow meets all the flow requirements, doesn't burst any pipe, and achieves the full capacity of the, is going to be the maximum possible flow in the network. Okay. So what we proved then is that if we solve this network flow, we construct this network flow, we solve it. If we get a solution, okay, then that gives us an assignment, and we're good. Okay. If it says no, here's the max flow, but it's not good enough, then we say, oh, well, in fact, there is no way of assigning patients. Doctors, you're going to have to be less fussy. Change your requirements. Okay. So does this? Okay. So let's abstract what we're doing, what we did in this problem, and talk about, in general, how do we use one problem to solve another problem? What were the different ingredients that we needed? Okay. So first I need to say what kind of problem we're talking about. So I'm going to have, say, two surge problems, pi 1 and pi 2. Okay. And they have our generic format for surge problems. We have some notion of what an instance is, call it I1, a possible solution, S1, and then we have some condition that S1 and I1 has to meet for this to actually be a valid solution. So we have a relationship, R1, between I1 and S1. Okay, a relation that has to be true for this to count as a valid solution. So the problem is to, if possible, find an S1 so that R1 of I1 S1. And problem pi 2 has the same format. I'm just going to change all the 1s to 2s. So it's got some notion of instance, I2, some notion of solution, S2, and some constraints that I'll call a relationship, R2, between I2 and S2. And we want to map this problem into a special case of this problem. Problem pi 1 is a special case of problem pi 2. So what I'm going to just say is, let's take what we did for this particular problem and generalize it into what we have to do for every problem, for this kind of arbitrary problem. Yeah. Sorry. Oh, this is supposed to be an I. And this is also supposed to be an I. Okay. So we had three ingredients that we needed in our reduction from the patient problem to network flow. Let's try to write down the analogous thing. in this abstract framework. So one, so we from our input to the patient problem, we constructed an instance of network flow. So what's the generic version of this?
Find the mapping which transforms instances of one problem in instances of the other one.
Yeah. We just have to keep clear which one we're starting with and which one we're mapping to. But so we want to make this problem a special case of this problem.
So I1 is equal to something of I2.
Yeah. So we have define some transformation. I'm going to call F. That takes I1 and produces I2. And this F needn't produce an arbitrary instance I2. It just has to produce some instances I2. Okay? So it needn't be invertible at this stage. Okay. So that's what we did in this first step. From RI1, which was an instance of the patient study problem, we created an instance of the network flow problem. And that allows us to define all the ingredients. In this case, we sort of embedded the I1 into I2, but in general, we can define it anyway by any rule that we want, as long as this F is efficiently computable, because we actually have to do it as part of our algorithm. Okay. So, what was our second ingredient? We said, well, if there was a flow that met all the requirements of flow, then we could use that to create a solution to our original problem. Okay. So what does that correspond to in the generic terms? So if I1 is the medical studies problem, I2 is the instance of network flow. Okay. The flow is a solution to I2. So that's a possible S2. Okay. And we need to from such an X2, what do we need to construct?
S1.
S1. So we need to take a map G that says, given S2, how do we construct S1? And then we need to prove something about G, about this construction. Here we just needed to prove, have it be some instance. We hadn't actually proved anything about that instance. But here we need to prove something. So the part A is to define it. And then what do we need to be true?
Meets the constraints.
So the constraints are the same. Or at least if this is a valid solution, then this is really a valid solution. So we need to show that if S2 is a valid solution in the sense of the second problem, then S1 that we construct by the map G is a valid solution in the sense of the first problem. And for this, we need to actually remember what the constraints are here, list them all, know what we have to work with, list the constraints here, and prove them one by one.
What's the R short for?
R is the relationship that has to hold to meet all the constraints. So R stands for a relation. Was that the question, or? Okay. Okay. And then there's the part that everyone forgets, because we don't actually. So it's important that F and G be efficient, because they're going to be part of the algorithm. Okay? Here, there's a final part that we have to do to prove that the algorithm is correct that actually isn't used anywhere in the algorithm. And that's to say, if we say, this says, if we find a solution S2, then we get a good solution S1. But what if the algorithm for this problem says, nope, there is no solution S2? Then we have to say, nope, there was no solution S1. And to show that that's valid, it's often easier to go in the reverse direction. Say, if there were an S1, then there would have been an S2. Okay? And to do that is often easier, the easiest way to prove that if something exists, then something else exists, is to actually give the construction. So what we need to do is define a map that works in the reverse direction. It takes an S1 and produces an S2. And then we need to prove the analogous thing in the reverse direction. That if R1 of I1S1, then R2 of I2 H of S1, which is how we're constructing the S2.
We also need some kind of analogous F mapping that gets us I2
So
from I1.
we don't actually, and so we don't need to be able to invert this F, okay? Because actually, so we need the existence of solution to be in one to be equivalent to the existence of solution in the other, but we're saying that this problem is a special case of this problem, okay? We're not saying the problem pi 2 is a special case of pi 1. So we're not necessarily saying the two problems are equivalent, so we don't necessarily need to be able to invert that mapping. And most of the time, or much of the time, there might be no easy way. The mapping might be far from onto. It might be a very special case. So we're not arguing that every network flow problem comes from this patient problem, just that every patient study problem can be viewed as a special case in network flow. And so, okay. Okay, so if we've got to this kind of reduction that has these three kinds of mappings, then, and we've got an algorithm for pi 2, then we can construct an algorithm for pi 1. So, if we have F and G and H as in this generic picture, and A2 solves pi 2, means finds a solution if it's possible, then we can define A1 that's going to solve pi 1 in the same sense. Find a solution if the solution exists, as follows. So we let I2 be our construction of an instance of pi 2 using this transformation F. S2 gets our best attempt at our solving I2. If S2 is a solution, we return G of S2, and otherwise, if S2 is just the message, no solution exists, we return the message, no solution exists. So, if I2 is solvable, A2 by definition finds it, finds a solution, S2, and then this map G converts that to a solution for original instance, and so that's what we want. But the guarantee is that if I2 is not solvable, then I1 can't be solvable either, because if I1 were solvable by some solution S1, H would have mapped it to a solution S2. So there would have been a solution. So if we can't find, so H is never actually used explicitly in our algorithm, but it's important because otherwise this line would be incorrect if it weren't possible. So, okay. So what's going to determine the running time of A1? So it's going to be, so there's going to be F and G. The time to compute F, observed polynomial time solvability. So if we don't care, so this is the exact time, but all we care about is that each of these be polynomial time, then all that's important is that F and G be polynomial time. So if F and G are both computable in polynomial time, then we call this pair, and it reduces, and it meets all these conditions, then we call the reduction. We say that pi 1 is polynomial time mapping reducible to pi 2. Or sometimes, I guess, so this stands for mapping, meaning we're mapping a single instance of pi 1 into a single instance of pi 2, and this P stands for polynomial time. And the important thing is that then, if pi 2 is also in polynomial time, and I'm going to use the class script P to stand for all the problems solvable in polynomial time, and pi 1 maps to pi 2, then what's also going to be true about pi 1 is polynomial time as well. So this kind of reduction, polynomial time reduction, preserves being in polynomial time. If this algorithm A2 is polynomial time, then the algorithm A1 we construct is polynomial time. Okay. But we can also use this as evidence that pi 2 is, so this is, what we've been doing so far is using this as a way, reductions, as a way of showing that problems are easy by reducing them to problems we know how to solve. We can also use this as a tool if we can reduce a problem that we know is hard to a problem that we don't know anything about yet. We can use this as a tool for showing that that problem is hard. So how about if we know that pi 1 is not solvable in polynomial time, or we believe that pi 1 is not solvable in polynomial time, then what can we conclude from this? It's logically equivalent.
So pi 2 is not.
Pi 2 is not in polynomial time. But we have to be a little bit careful. What if we know that pi 1, we know how to solve pi 1 and we reduce it to pi 2? What can we conclude about pi 2?
That is thinking.
Think about it. So we've taken the easy problem, we reduce it to an unknown problem. What can we conclude about the unknown problem? Well, you might like take a problem, an easy problem, view it as a special case of a hard problem, but the reduction doesn't go the other way. It's not. Just one instance is easy. Okay, some instances are easy. So what does that really tell you about pi 2? Nothing. Okay. And the only reason why I'm making a big deal about it is that people do get confused. Okay? We reduce a problem. Actually, this happens implicitly all the time. We take our problem, we say, oh, wait a minute, if I look at this in a certain way, this is an independent set problem. An independent set is hard. Therefore, my problem is hard. That actually doesn't follow. Even if viewing it makes it an instance of independent set is hard in the worst case. It's not hard every case. And so the class of instances that you're talking about might be easy instances of independent set. Actually, I'm going to show you maybe one in a second. Okay. And how about if we know that pi 2 is hard, what can we conclude about pi 1?
Nothing.
Nothing. So there are two ways of using reductions validly, and two ways of using them that don't get you anything, or two ways of potentially misusing them that don't actually tell you anything. Okay. So let's give. Okay. Well, actually, before I go back and give one example. One more example using network flow. Let me define at least, now that we have this abstract framework, we have like 90% of at least the definition of NP. So here I have this kind of generic format for a search problem. Let's say, if we want to be able to solve a search problem, have a fighting chance of solving a search problem in polynomial time, there's certain minimum conditions that should follow, that we should have. Those conditions don't imply that the problem is solvable in search polynomial time. Just that it's not crazy to think that it's solvable in polynomial time. So solvable in polynomial time means solvable in, say, like the number of bits to represent the input. So if we want to produce an output in time polynomial in this number of bits to represent the input, what had better be true about that output? It's polynomial in length. If it were an exponentially long output, there's no way we could actually even write it down in polynomial time in x. So the number of bits to represent s had better be less than some polynomial in n. And almost all the problems that we looked at, this is true. Yes?
Why don't we choose bits instead of another representation?
Because any kind of valid representation, if you look with dead base 10 or so on, those are all going to be related within a constant factor to bit. Any other base is going to be related to within a polynomial factor. If you look at things like arrays of real numbers, and they have infinite precision, then the dimension of that array won't be related to the number of bits. And we said that sometimes that actually makes a difference. And when we want to look at that difference, we want to actually talk about number of bit operations rather than just number of real number operations. When you start not counting, if you can't really count it as bits, then I want to argue that it really shouldn't count. It's just an abstraction that does it. When you convert it to actual computer program, run it on an actual computer, it has to be translated into bits. And so therefore we counting bits. Other reasonable representations really aren't going to change the number of bits by more than a polynomial factor. Okay, how about this constraints R1, I1, S1? So like, if you couldn't even decide, given a solution, whether it was valid or not, is there any hope of finding a solution? Not really. So the other condition is that we want the constraints to be, you'd be able to check the constraints in polynomial time. So if someone gives you a solution, does all the work of finding the solution, you can verify that solution in polynomial time. So if a problem pi1 has these two properties, then we say that pi1 is an NP search problem. So NP is the class of search problems. And I'm being a little bit misleading. Technically, it's a class of related decision problems rather than the search problems, but it's equivalent to, okay, within polynomial time solvability, it's equivalent to what I'm writing down. So it's the class of search problems that meet these conditions. So NP, I should point out that NP does not stand for something like non-polynomial. It stands for non-deterministic polynomial time. I'm not going to try to explain what that means. But one thing it doesn't stand for is not polynomial time. The n is not the negation of polynomial time. Things in NP include all the search problems that we've given. NP includes all the search problems that we know how to solve in polynomial time. In fact, it includes any search problem that you can solve in polynomial time. So P, the polynomial time solvable search problem, is a subclass of NP. And the P versus NP question then is whether there are anything at all that meets these basic properties that can't be solved in polynomial time. That maybe require exponential time to solve. So anything in NP you can solve by brute force in exponential time because the number of bits in a solution is polynomial. So an exponential in that polynomial, you can go through all the possibilities and you can check each one in polynomial time. So any problem in NP is solvable and exhausted by exhaustive search in exponential time. And the question is, can we actually bring that down to polynomial time, or are there some problems in NP that really require superpolynomial time? So are there any hard problems in NP? So this is a very abstract question because you have this just two generic format. You say, well, there's a huge number of possible problems in NP. How could we even reason about whether any of them are hard? Fortunately, there's this notion of NP-completeness that says certain problems, so that sort of like network flow was important because it had some expressive power. We could reduce other problems to it. Saying, let's go to the ultimate in expressive power. Saying something is NP-complete if not only can we reduce some problems in NP to it, we can reduce any problem in NP to it. So we'll say search problem pi is NP-complete first if it's in NP but the second condition is that for every other problem in NP we can view that other problem as a special case of pi. So if pi is NP-complete, then this abstract question of whether, maybe I should say P, of whether the class of polynomial time solvable problems, search problems, is equal to the class of all problems that is sort of our candidates for polynomial time solvability, is just equivalent to whether this single problem is polynomial time solvable. So an NP-complete problem encapsulates in one particular problem this whole class of abstract search problems. Well, you should be asking, well, that's nice, but do these problems exist? And what do they look like? So not only do they exist, but they're all over the place. And in fact, we've already seen a fair number of them. So, so examples of NP-complete problems. I think like the canonical example are different versions of satisfiability, where you're given a circuit, you want to know whether there's some input which makes the circuit true. But there are also other much more combinatorial problems, like maximum independent set is NP-complete. Three-colorability is NP-complete. Hamiltonian path. The two-machine load balancing problem is a numerical problem that's NP-complete. And the list goes on and on. Yeah.
For what you had said over there, it means that here also pi prime is NP-complete.
No, well, so pi prime reduces to pi, but if you have pi reduced to pi prime, then pi prime would be NP-complete. So here, pi prime could be easy or hard. Okay. But it's, whatever it is, it's reducing to pi. Whatever problem we're talking about, easy problems reduce to NP-complete problems, hard problems reduce to NP-complete problems, other NP-complete problems reduce to NP-complete problems. Okay.
So I have another question.
Yeah.
How do you show that one problem is NP-complete?
Okay, so there's one tricky part where you have to establish that there's one problem that's NP-complete. But once you have one problem that's NP-complete, you can start chaining the things together. Okay? So because reductions compose, yeah. Maybe I'll answer your question in a minute.
Okay.
Okay. So if we have pi 1 that's NP-complete, we know that it's NP-complete. And pi 2, pi 1 reduces to pi 2. And I guess technically we need to show that pi 2 is in NP, but that's usually pretty easy. Then pi 2 is NP-complete. And the reason is that if pi 1 is NP-complete, that means every pi prime reduces to pi 1, but pi 1 reduces to pi 2, and by composing these reductions, we get a map from every pi prime to pi 2. So once you have one NP-complete problem, you just have to show that you can map an arbitrary instance of that problem to your new problem to show that your new problem is NP-complete.
But I still have a problem with this, because I don't know if it's a matter of notation, but this doesn't match with what you have said over there. So there you had the pi2 that was in P, and this property was transferred to pi1 on the left.
That's right. But so saying easiness goes from pi2 to pi1. NP-completeness is hardness. So hardness goes from pi1 to pi2.
Okay.
Okay. So you have to keep those two directions straight. So hopefully, I think I didn't make a mistake this time, but it's very easy to make a mistake and reverse the direction of reduction.
How do you know that all problems will reduce to another problem?
Okay, so okay, to get started, we actually have to define rigorously what we mean by an algorithm. Okay, use a model like Turing machine. Okay, and then say here's how to a generic way of reducing an arbitrary Turing machine to a particular problem. Okay, let me give. I guess I was going to give another example of using this approach for network flow. Well, let me instead give a sketchy proof for how we would get an NP-complete problem. So, so this is kind of this one seems like a cheat because it's sort of like pushing the genericity into the problem. Okay? That's how we get started. Okay? So the circuit satisfiability problem is the instance is a circuit, a Boolean circuit C that has inputs, Boolean inputs x1 through xn. A solution is an assignment that says for every xi it either has value 0 or 1. So this is going to be expressible with more than n bits. Solution just requires n bits, 1 per input. And then the constraint is just that C, when we plug in A1 through AN, should output, say, 1. So this means that the A1 through AN is a satisfying assignment for the circuit. So how do we reduce an arbitrary problem to the circuit satisfiability problem? Well, our reason, and you have to make this formal, is that take any kind of relationship that can be verified in polynomial time. Okay. Well, when you run an algorithm for polynomial time, what actually happens at the hardware level? You know, the software is running for polynomial time, but each software instruction gets translated into a hardware instruction. Okay. And each hardware instruction gets translated into a certain set of Boolean operations. And so what we'll just do is have the circuit simulate the Boolean operations that we would go through in verifying a solution. Okay. So we just like interpret the algorithm that it would take to verify a solution as a circuit. And have the bits x1 through xn be each bit in the solution. And then we say, well, a way of making the circuit output 1 is equivalent by our construction to a way of setting these bits of S1 to make R1 of I1 S1. And that's how we constructed the circuit. That's our F, and then the actual map between the solutions is just the identity map. Use each a bit in the assignment to define a bit of the solution of the original problem.
In that case, do you not need to go through these steps?
Well, I'm just saying that we still need the 1, 2, 3. One is the hard part, the G and the H are equal to the identity. You just take the solution and you map it back and forth, and it's just by construction, is the constraint, satisfying the constraint for one is by definition satisfying the constraints for the other.
In that case, can you like give a definite runtime?
We don't know how to solve circuit sat in an efficient way at all.
Okay.
So the hard part is saying, well, now you have to have a good algorithm for circuit sat. So the circuit we construct is going to be sort of proportional to the time of this algorithm, because it's a translation of the algorithm that we use to verify the constraints at the hardware level. So that, as this complexity grows, the size of the constructed instance grows. The rest is just identical. Okay. But then we can take circuit sat, and actually circuit sat has this, even though it's kind of an arbitrary logical sequence of operations, that sequence gives us a sort of combinatorial handle on the operations. We can start reducing circuit sat to things like independent sat by having a gadget representing each particular Boolean operation in terms of the independent set in a little subgraph. And maybe next class I'll show you how to reduce circuit sat to something like independent sat. Yes.
You can make sort of a historical argument about why circuit sat was the first NP-complete problem demonstrated. I'm just wondering if you can imagine any other scenario where what the
actually we actually did this experiment in parallel because the notion of NP-completeness was discovered independently in Russia by Leonid Levin, and his first problem wasn't circuit sat, it was silent. So that would be the other one.